Hi there. Thank you for clicking on this video where we're going to cover applications of quadratics. So please give this video a thumbs up if you find it helpful, subscribe for more math content, and check out the practice work for this lesson along with some of the other videos and playlists on the channel. So this is going to address what can we do with quadratics. If you have been studying quadratics, you have looked at their graphs, you've looked at key points, you practiced factoring and solving equations in the quadratic formula, all this stuff. Why? Why do we do this? What do quadratics model outside of math class that this is worth studying? Well, they actually model a lot of things, but the most common one to practice with are problems that involve something called projectile motion. Now, this is a great place to start. It's where we're going to focus this lesson. If you go on and take further math classes or you take a physics class, you will see other applications. Kinetic energy is one that comes to mind. Okay, that's also an application of a quadratic. But we're going to start with projectile motion. Now, projectile motion is when an object is tossed, thrown, or launched. And a key fact about projectile motion is that the only force acting on it is gravity. So there's no, engine attached to it that's going to cause it to continue to accelerate. And everybody, by the time you've taken an algebra class, you've thrown something. So you have a ball in your hand and you throw it up and then it hits the ground somewhere, okay? And that would be projectile motion. When I teach this in my classroom, I will often throw something across the room, just like, hey, reminder, this is what it is. And the motion doesn't just look like a parabola, it is a parabola. Now, in a physics class, you could get more into the nitty-gritty math stuff, like what if there's air resistance? What if there's a draft in the room or a fan blowing? Yes, that would affect the motion, but that is not where we start when it comes to applying this. And most of the time, if you just are throwing a baseball, it's going to follow the physics and the mathematics of projectile motion. Now, there's two different ways we can do this, and it has to do with what's on the x-axis. So if I were to superimpose the coordinate plane on here, and I put the y-axis right through the person, and I put the x-axis along the floor, this would be looking at horizontal distance. Being on the x-axis, like how far away from you did the ball land. But it also works with time. Okay, and that has to do with the way gravity works. Again, probably saving it for a physics class. And the problems we are going to look at in this lesson, we're going to use time. Okay, so we're going to put time on our x-axis. Typically, I find more students are comfortable with that, and it really doesn't change anything significant about how you would do the problem. It would change the way questions were asked, or which questions were asked. And I'll try to remember to give you an example of that when we look at the different kinds of questions. So what kinds of questions are we asked? There are about 5. I say about because I don't want to exclude the possibility that your teacher might come up with a different kind of question. But basically, there are 5 things that you can be asked when dealing with projectile motion. Now, this little part right here, this is a disclaimer. For the purposes of instruction, the numbers have been simplified in the lesson. Real-world numbers are studied in a physics class. So in a math class, generally, you are given the function. You're given the quadratic function. In a physics class, you would need to write the quadratic function because you would study the what gravity is and how it plays a role in that motion, and it would be up to you to figure out where the different numbers go in the equation, and that would be for a different class. When we are studying this for the first time in a math class, the function is given for you. And we tend to simplify the numbers so that you are able to focus on the concept. How does this apply? So if you are in a physics class, physical science class, and you look at the problems we're looking at and saying, she's using the wrong numbers for gravity, I am aware of that. I love physics. Okay, started college as a physics major before I ended up switching my major. So I am aware that the numbers, like we have messed with the numbers. You say, well, gravity should be 9.8 meters per second squared. Like, I know that. We're not going to use that number because we want to kind of keep our focus on the concept and not get muddied up with very, very messy numbers. So this is our example problem. You are playing fetch with your cat and you toss a milk bottle cap across the room for her to retrieve. So you're sitting on your couch, you're sitting on the floor, or wherever you are. And you got a milk bottle cap and you throw that milk bottle cap across the room. The motion of the cap can be modeled by h of t equals negative 0.5 t squared plus t plus 3.5, where t is in seconds and h is feet above the floor. And we have a photo of the most beautiful cat. If you don't think she's beautiful and adorable, you're wrong. And she wants to play fetch with us, which is her prerogative. Now, a few things about this notation before we move on. This h of t, what does that mean? It means that the height of the cap depends on time. Okay, that's what function notation tells us. In fact, we would say h of t, meaning height is a function of time, or it depends on time. How high that milk bottle cap is depends on how long it has been since it left your hand. Now, you can just do this, and I will tell my students this. If the function notation really bothers them, you can just say h. You can say height is equal to, the height of the cap is equal to that, okay? It's the same thing as if you said h of t, okay? It just maybe is a little bit cleaner. Or if you wanted to go back to our generic x's and y's, you could sub out the generic x's and y's, or you could say f of x, okay? All of that is simply notational, so don't let that notation throw you off. And we are told the units, okay? So we're going to measure time in seconds and height in feet. Last thing about that is I have seen these application problems where a lot of like unnecessary information is given in the problem. And so you might be told like how high it is when it starts, or you might be told the initial velocity, or some other fact. Typically, you don't need that information. I'm not going to say like for sure you don't need it, but if you are given that stuff, don't let it throw you off. Focus your attention on the function, okay? Because that will tell you everything that you need to know. Everything you need to know will be in that function. Remember, I said it's in a physics class that you would study how to put the function together, typically not in a math class, okay? All right. That is my cat, by the way, in case you were wondering. All right, so what are the 5 questions that we might be asked? First question, and you're going to say, but wait a minute, you just gave us 3 questions there. Yep, I kind of brainstormed what are the different ways this question could be asked, but this is all the same question asked 3 different ways. What was the starting height of the cap? From what height was the cap tossed? Or how high was the cap when it was tossed? And that is not exhaustive, so we could come up with other ways, but basically it's saying at the moment that the cap left your hand, how high above the floor was it? Okay, so all the, like the same question. It's like if I were to say, what is your name, or what are you called? Okay, that is 2 questions. It's the same question. Okay, 2 ways of asking the same question. So that's one of the questions you might be asked. Second, how high did the cap go, or what was the cap's highest height, or what was the maximum height of the cap? So that would be another question, and you want to home in on stuff like maximum height. That is a key key vocab right there. So how high did it go? So when it left your hand, the cap went up. It went up for a little bit, and then it came back down. How high did it end up going? Third question, when did the cap reach its highest height? Okay, and once again, we see this maximum height or highest height. Okay, we see that in both of those problems, highest height, maximum height. How long did it take the cap to reach its maximum height? When you see that vocabulary, that is a tip off that you're dealing with the vertex. So remember our little stick figure there. Okay, there goes the milk bottle cap, and we're talking about the highest height. That is going to end up being the vertex of the parabola. But notice that there are two different questions that you might be asked, both of which are going to require knowledge of the vertex. Fourth question, how long was the cap in the air, or when did the cap hit the floor? So that is your fourth question. And if you were dealing with that horizontal distance instead of the time, it could be where does the cap hit the floor, or how far from the cap, how far is the cap from you when it lands? Would be different variations on that. And then the fifth one is how high was the cap after 0.5 seconds, or what was the height of the cap when t equals 0.5. This is a specific, like finding a specific point, and I just picked 0.5 seconds. I could have picked something else, okay? But you could be asked to identify a specific point, okay? Now, I'm not going to say that's an exhaustive list of the 5 like things that you could be asked, because your teacher could come up with something else to ask you about it. But the vast majority of the time, you are going to be asked one of these things, maybe all of these things, maybe 2 or 3 of them. I don't know. But it's going to be one of these things here. Okay. Can't guarantee you that, but it's pretty safe bet. So we're going to look at how the graph shows us this motion. And one of the great things about starting your applications with projectile motion is the fact that it is so visual. We can all picture the object moving through the air and making that parabola. And you'll notice that I did label what we were looking at. So we have height on the y-axis measured in feet and time on the x-axis measured in seconds. And the actual trajectory of the cap, the milk cap, is that right there. All right, now let's kind of think about why that's true. If you look at your x-axis, okay, on the x-axis, we are measuring time. As soon as I go back this way, I'm in negative time. So this is like -2 seconds, -4 seconds. That doesn't make any sense. If we were dealing with horizontal distance, this would be like if you threw the cap in back of you, or you threw it forward and it landed in back of you. So this, just so we can kind of, okay. All right, that is like, I don't know why your neck is so long, but okay. So you're standing right there and you're throwing the cap, okay? The x-axis represents the floor, because when you look at this point right here, okay, remember that our x, y's, our time is on the x and height is on the y. So you're like x, y ordered pair is time, height, and here the height is 0. Well, what does it mean if the height is 0? It means it hit the floor or the ground, okay? Or the lowest point, like the height is 0. If it goes below that, then like it is burrowed into the earth, okay? And I don't know what kind of milk you're drinking, but wow. All right. So looking at this, okay, what is the starting height? Well, the starting height would be when the time is equal to 0. So we would be looking over here for when the time is 0. And we can see when the time is 0, the height is 3.5 feet. So you are throwing this from a height of 3.5 feet off the ground. So maybe you're sitting on the couch and you're like tossing it from that height, okay, but it starts at 3.5 feet above the ground. The maximum height. Now remember how we have this set up. We have time is on our x-axis and the height is on the y-axis. So when we look at that ordered pair, the 1 represents the time and the 4 represents the height. And so you could even think of that as 1 second and 4 feet. That is our ordered pair. So what is the maximum height? The maximum height is going to be at that vertex, and the height there is 4 feet. So it goes up 1/2 foot, all right, from where it started. So it started at 3.5 feet and it just went up a little bit. Okay, it went up to 4 feet. When is the maximum height reached? So I said earlier, like you've got these 2 different questions that both require you to look at the vertex. One of them is what is the maximum height? That's going to be the y coordinate. And when is the maximum height reached? So like how long did it take to get up there? That's going to be our x coordinate, and that will be 1 second. So 1 second after leaving your hand, it reaches its maximum height. Now, realistically, okay, remember I said I messed with the numbers to kind of make them a little bit nicer. That's a long time for it to reach its max height. Okay, if you think of like 1, it was, I don't know, just kind of look at a clock, like that's a long time. But it's a nice number. Okay, for this. Now, when the cap lands, okay, so when does this cap land? So here's the trajectory. It goes up and then it comes down, and right here, the height is 0. And so we want to know what was the time when the height was 0. Well, it was 3.8, we'll just say 3.83 seconds. So that took 3.83 seconds for that milk cap to hit the floor, because that's where it hit. And then this last one does require a little bit of calculation, and I did put the function down here so that we had it. It was, what is the height of the cap at 0.5 seconds? Now, if I look at this, this is where 1 is, this is 0.5. If I go up from there, you can get a pretty good idea of where it is. It's not all the way up to the 4 feet because it's not going to be quite there. That's not a straight line though, so you cannot assume it is exactly halfway between, because it's not a line. But what you could do is plug it in. And so we've got the height of the object as a function of time is this. And then what we're going to do is plug in 0.5 for t. And so this will be 0.5 squared plus 0.5 plus 3.5. And we're going to need to do that on a calculator. Okay, plus 0.5 plus 3.5. And I messed up my calculator, so I love that. I love how I did that right while I'm recording. So we'll try again. Here we go. All right. Plus, we'll just add 4. 3.875. All right, that's supposed to be a parenthesis. Okay, so h of 0.5 is 3.875, and that would be in feet because it was a height. And what that means is after 0.5 seconds, this is how high it was. And you could do that for any amount of time. So your teacher could like give you any time. Now, if your teacher gives you like a negative time or something, you're going to end up in this piece of the parabola. Well, you see there is another x-intercept back there. It's just not meaningful because this would be like going backwards in time. So you always want to be mindful of that as well. For the purposes of this problem, like the part of the parabola we're interested in is never negative, okay? So there you go. You just kind of read them right off the graph. Okay, so what if you can't graph it? All right, what if graphing it is not one of the options? This is where your algebra skills kick in. If you need to find the starting height, you're going to set t equal to 0 and then find h of 0. That's actually going to be fairly simple to do because starting means at the beginning, so time is equal to 0. So whatever that function is, okay, so we had this plus 3.5, and we're going to plug in the 0, and I love zeros. They're the best. And we end up with h of 0 equals 3.5, or the c value. Okay. To find the vertex, you've got a couple options. Use x is equal to the opposite of b over 2a for the x coordinate, and then plug that into h of t for the y coordinate. Or you can complete the square to put it in vertex form, but I do not recommend that because too many functions, like putting it in vertex form is not going to be good. But it would look something like this. So we would do the opposite of b. So that would be -1 over 2a. So this ends up being -1 over -1. So that's going to give us the x coordinate. And then we would plug the 1 in. So we would do h of 1. So that would be -0.5 plus 1 plus 3.5, which is 4. Okay, so you can find the vertex that way. Now, to find the landing time, okay, or the x-intercepts, you're going to set the height equal to 0 and then solve by either factoring or the quadratic formula. And I'm not going to go through that because this video is already long enough, but what you would do in that case is your 0 would come over here, like so. Okay, and then this one you would probably use the quadratic formula, and we know that that had like nasty decimals, so that it would be a quadratic formula problem, and you'd use the quadratic formula and you would just toss out the -1 because it wouldn't make any sense. So if you can't graph it, now you've got to fall back on your other algebra skills. Are there any tricks to this? Well, I'm not a tricksy kind of person. To channel my inner Gollum, just if you're a Lord of the Rings fan, you know what it is to be tricksy. No, I'm not a tricksy person. So no, not really, but projectile motion is very visual. So if you have access to a graphing utility to help you identify the points you need, do it. Okay, so go ahead and graph it because that parabola that you see on the graph is going to very closely mimic what you see in real life when you throw the object. And so that will help you identify the right points. So that's what I would say to do. All right, that was it for this lesson. Please like this video if the lesson was helpful. Subscribe for more math content. Drop a comment to engage or ask a question. And please check out the practice problems for this lesson so that you can reinforce how we apply quadratics to projectile motion.